Okay, so to start us off on this unit about gases, I wanted to do a quick little reminder about what a gas is. So, as you can see, the main thing here is that gases have particles that are spaced really far apart. And like we did in class, they are moving, right? We have little arrows showing that they are moving around. So, a solid would have particles that would be very, very close together. They'd be very, very compact and ordered. And this means that these things are really, really dense. Gases are not dense. They are really spread out. There is a lot of space here, which means that they take up a large volume compared to their actual mass. So they have small densities. They're constantly moving, right? So this isn't vibration. This is lots of motion. And that motion happens to be very fast motion. And that's really, really important. Because as we're going to find, one of the things about gases is that they can kind of change speed and change direction. So they are also compressible, right? We can squeeze them together a little bit. And they can take any shape and any volume, right? This is the only type or state of matter that can actually change its volume. Okay, so how does that mean that gases actually create some amount of pressure? Well, as you can see here in these two different diagrams, we often use those arrows to figure out or to show speed. So if you've got a short arrow, that means you've got a slower speed than if you have one of these longer arrows, which is going to be a higher speed. So the thing that actually creates pressure is two things: how often a collision occurs, and then also how hard a collision occurs. So you really have to think about the gas and think about when you're changing different aspects of the gas, which of these two things is going to be affected? Are you going to change how often collisions are happening, or are you going to change how hard those collisions are happening? So if you make collisions happen more often, well, more collisions equals more pressure. And then the opposite would also be true, right? So more collisions equals more pressure. And I'm just going to use P for pressure. And if you have harder collisions, well, harder collisions also mean more pressure, which is also very important. So the whole next section 8.2 deals with changes in those two things, the how often and how hard, and what that means for pressure. So that's important in that regard. Okay, switching us over here to this PhET simulation. So right now in this PhET simulation, we've got a gas going on, and we've got a temperature of about 78 Kelvin that you can see up in the thermometer, and a pressure that's floating back and forth around 20 some odd atmospheres of pressure. Now, there's a couple of things we can change here that allows you to see that impact on pressure. So if I heat it up a little, right, the temperature is going up and you can see the particles are going faster. They are colliding more often and the pressure is going up. That should make sense to you. I can also come over here and I can pump some more gas into here. I am adding more particles. If I am adding more particles, that is also causing more collisions, and indeed my pressure does go up. Another thing I can do is I can actually decrease my volume. I can squish these guys slightly closer together, compressing them together, and by doing that I'm making collisions happen more often, also making my pressure go up. So I freely invite you to go to the website and play with this thing as much as you want, especially when you're starting to go over the individual gas laws. It's really helpful to play with this diagram. Okay, so I want to talk about atmospheric pressure, and then we'll talk about individual pressure. So in atmospheric pressure, you may not realize it, but when you are standing on the ground, when you are this person right here, so say you are in DC, we're practically at sea level, you have millions and billions of little gas particles that you cannot see bouncing off the top of your head over and over and over again. So it's all of these tiny little particles hitting your head that are producing what you feel as pressure. So atmospheric pressure is actually gas particles colliding with you. And the closer you are to sea level, the more gas particles you have above you banging into your head. If you were higher up, say you were up here in like Denver or something, the Mile High City, and you're all the way up here, well, you're above a lot of those gas molecules, and therefore you don't have as many, and since you don't have as many, you don't have as much pressure. So that's why at the top of mountains you're going to have low pressure, and at the bottom you're going to have high pressure. And that's going to affect all sorts of things. If you blow up a balloon at sea level, you're going to have a fairly small balloon, right? We've got the small balloon. But if you take that balloon all the way up here, well, that's going to turn into like this bigger balloon, and it's going to turn into a bigger balloon because there's not as many things pushing in on it. So here you've only got like a couple of things pushing in on that balloon, but down here you've got a lot more particles bouncing in and squeezing in on that balloon. So that's kind of how you need to think about atmospheric pressure. It always is present. Okay, so it's always present. And in AP chemistry, we typically say that atmospheric pressure is 1 atm, all right, or 1 atmosphere. And that is our most common pressure unit in chemistry. So when we look at that, what that means here is that to measure atmospheric pressure, we need something that's open to the atmosphere. And so we have a thing called a barometer. Now, this is an old Mercury barometer. And these things are old, and you're not really going to see them anymore. Most of what you see now, barometers, are like these little dials, and it basically just reads off a thing like this with little tick marks all the way around it. I have a barometer like that we'll use in class to measure the atmospheric pressure when we do a lab when we get back. But the mercury barometer is what was originally developed. So what you have here is you have a pool of mercury, and it's open, right? It's open to the air. And because it's open to the air, again, you have all of these tiny gas particles pressing in on that mercury. And since you've got basically like a giant straw, this is a big glass tube, a giant straw here of mercury, it's forcing that mercury up that tube. It's pushing it into the tube, and it pushes up and it pushes up, and it can support certain amounts of mercury in this tube depending on how much pressure there is. So more atmospheric pressure equals a higher amount in the tube. And that should make sense to you because there's more stuff pushing down on there, pushing up into the tube. So they literally took like a meter stick and had a meter stick off to the side of here, and it had all these tick marks, and you could measure and say, okay, so the atmospheric pressure is holding up a column of mercury that equals 760 millimeters, because remember metric system, of liquid mercury. and that is equal to 1 atmosphere. So you'll see barometers and things like that using slightly different measurements. Normally this millimeters of mercury, because it's a throwback to the original type of barometer. Now, this would not be a very practical lab tool, so we have a different way of doing things in the lab. In a lab, we're going to use something, called a manometer. And a manometer is used to measure any gas. And you measure it by comparing to atmospheric pressure. Okay, so this is your general thing. So you would have, this is all sealed off, and you have your gas in here. And right now you see how these are equal? The height, this is a little bit of mercury that's sitting there in that little J or U tube. And if those things are equal, that means right there that in this example, the atmosphere is equal to the gas. They are the same amount because these are equal. In the other examples, you have to think about, this is a battle. It's a battle between pressure and who is winning, all right? So you're going to have the atmosphere pushing on one way, and you're going to have your gas sample, over here pushing on the other way. And depending on where this mercury is sitting in that tube is going to give you the eventual winner. So here, who's pushing harder? Well, the atmosphere is pushing harder. So that means here that the atmosphere is greater than the gas. So that means how much greater? Well, it's 140 millimeters greater. So how are you going to know what the gas is? Well, if the atmosphere is greater, then you're going to subtract off that amount of mercury. So you would have 760, which is your atmospheric pressure, minus 140, right? 760 minus 140, that would be 620 millimeters of mercury in this gas tube, okay? Because it clearly has less. It's losing the battle. So same thing over here. If I've got my gas over here, who's winning? This little bit of atmosphere or this lots of gas? Well, here in this example, you're going to have the gas beating the atmosphere because it's pushing in and pushing down on here. So that means that difference of 175 millimeters, well, you're going to add that to the atmosphere because it's 175 millimeters stronger than the atmosphere. So 760 plus 175. Doing my quick math there. 935 millimeters of mercury. Not bad. Okay, so for some practice problems here. These are similar to what is actually in your problems in the book. So it says, given a barometric pressure of 762.4 millimeters mercury. So that means my atmospheric pressure equals 762.4 millimeters mercury. Calculate the pressure of each gas sample as indicated by the manometer. Okay, so in sample A, who is winning? The atmosphere or the gas? Let's look. Who's pushing down harder? Versus this, I would say the gas is winning. So that means I'm going to add my pressure. So I'm going to have my 762.4 plus however much I think this is. Let's see here. Ooh, that's a tricky one to look at. So that is a difference of, it looks like 3.5 in each direction. So I'm going to say that's 7.0. Adding those together, 769.4 millimeters of mercury. And in example B, what do we have here? Who's winning? Atmosphere or the gas? Well, here I've got a much larger arrow on the atmosphere than I do on the gas. So I'm going to say the atmosphere is winning. So that's a subtraction. So again, 762.4. And how much am I subtracting off? Well, that looks to be just a bit over 2. Let's say it's 2.1 in each direction. Doubled, so that would be 4.2. And so let's subtract that off. 0.2, 8, 758 millimeters of mercury. Okay, in the next video, I'm actually going to do some pressure calculations for you, but this is just a basic idea of how we are going to conceptualize and think of pressure.